Yeah, so I'd like to work some exercises. Some exercises from section 7.2. So the first few exercises I'm going to work are going to follow up from theorem 7.9. Theorem 7.9 that we did in our fifth video. Our fifth video on section 7.2. So there's a video 7.2, basic properties of a group, part 5, and we want to follow up to theorem 7.9 there. So we're going to have some exercises. So here's an exercise. So let's suppose A is an element of a group G. And when we raise A to the 18th power, in other words, star A together a bunch of times, we have 18 copies of A. So A, 18 copies of A. And that gives you the identity. A to the 18th equals identity. So suppose this happens. What are the possible orders of A? So remember what the order of A is. A is the smallest power that we can raise A2 to get the identity. That's what the order of A is. The order of A is the smallest power that we can raise A2 to get the identity. So we know A to the 18 equals identity. Now, theorem 7.9 says that the order has to divide any power of A that gives you the identity. So the order of A must divide 18. So let me write that right. This is by theorem 7.9. 1. The order of A divides 18. And of course, it's positive, right? It's the smallest positive integer that you can raise A2 to get the identity. So thus, that means the order of A could be 1, because 1 divides 18. It could be 2, because 2 divides 18. It could be 3, because 3 divides 18. It can't be 4, right? 4 is not a divisor of 18. It can't be 5. Could be 6. No 7. No 8. Could be 9. Or it could be 18 itself. So those are the possible orders of A. 1, 2, 3, 6, 9, 18. Okay. So that's a follow-up from theorem 7.9, part 1. Okay. Here's another exercise. So this one says, suppose B is an element of a group G, and the order of B is 45. So what does that mean? That means 45 is the smallest positive integer such that B to the 45th equals E. Right? B to the 45th equals E, and 45 is the smallest positive integer for which that works. So what we want to do, we want to determine the following orders of the following elements. So what's the order of each element? So determine the order of B to the second, the order of B to the third, the order of B to the 6th, the order of B to the 12th, and the order of B to the 25th. Okay. So how do we find the order of B to the second? Good question, right? Well, you got to use your famous theorem. So let's go back to our theorem 7.9, number 3. So I'm going to write that here. This one's not in the book. This is one that I did in the video. so what does it say? It says the following. The order of a to the k is equal to the order of a divided by the greatest common divisor of the order of a and k. Right, that's basically what I had. I think I used n in place of the order of a. So if we're using that for the order of b squared, what will we have? We would have the order of b divided by the greatest common divisor of the order of b, and our power here is 2. That's going to be what? The order of b is 45, and we're going to find the greatest common divisor of 45 and 2. So what is the greatest common divisor of 45 and 2? 1, right? So we're going to take 45 over 1, which is 45. So the order of b squared is 45. Okay, let's find the order of b cubed. So we're going to take the order of b divided by the greatest common divisor of the order of b along with 3. So it's going to be 45 divided by the greatest common divisor of 45 and 3. What's the greatest common divisor of 45 and 3? It's 3. So 45 divided by 3 is 15. So the order of b cubed would be 15. So you'd have to raise b cubed to the 15th power, and that would be the smallest power to get the identity. Okay, how about b to the 6th? What's the order of b to the 6th? Well, it's the order of b divided by the greatest common divisor of the order of b, then 6. That's 45 on top, right? That's the order of b. What's the greatest common divisor between 45 and 6? Well, again, that's going to be 3. The largest number that divides 45 and 6 is 3. So, again, 15. 15 is going to be the order of b to the 6th. B to the 12th. Let's find the order of b to the 12th. So it's the order of b divided by the greatest common divisor of the order of b along with 12. The order of b is 45. What's the greatest common divisor of 45 and 12? Again, that's going to be 3. So 45 divided by 3 is still 15. Okay, we're going to do one more. That's the order of b to the 25th. And that's the order of b divided by the greatest common divisor of the order of b and 25. In other words, 45 divided by the greatest common divisor of 45 and 25. What's the largest number that divides 45 and 25? That would be 5. So 45 over 5 is 9. So that means b to the 25th has order 9. In other words, b to the 25th, the raised to the 9th power would give you the identity, and 9 is the smallest power that would do that trick. Okay, so a very nice use of that theorem 7.93. We'll probably make use of that later. Okay, so we want to go on to some other stuff. So here's an important fact. Let A and B be elements of a group G. Then AB equals BA if and only if. AB to the n equals A to the n, B to the n. for all positive integers n. Okay, so let's prove this. So we're going to start by letting A and B be elements of a group, G. We're going to begin with the red. So we're going to do the forward direction. We'll start with the red. So let's suppose A times B is B times A. And we're going to work towards the green. So we want to show this is true for any positive integer n. So let's let n be a positive integer. So if I take A times B to the n power, that just means AB a bunch of times, right? AB, AB, AB. In fact, we have n copies of AB. Now, because I can rearrange these, I can change the order. So basically the A and the B's commute, so I can change the order. That means I can put all the A's together and all the B's together. So I have how many copies of A? N copies. How many copies of B? N copies. In other words, I have A to the N, B to the N. Okay, so I've proven the green. Now going in the opposite direction, starting with the green and going towards the red, I'm going to assume that A to the N equals B to the N. So let's suppose AB to the N equals A to the N, B to the N for all positive integers n. So let's suppose it holds true for all positive integers n. That means that means AB squared equals A squared B squared. Right? If it works for all integers n, it has to work for n equals 2. Now we've done something very similar to this in exercise. Let me look at my book here. 24. We've basically done this exercise 24, but I'll just work it again. It's in a previous video. This means AB, AB, right on the left. And on the right, you have what? AA, BB. So what I can do on the left, I can multiply by A inverse, and on the right by B inverse. We have A, B, A, B, and do the same thing on the other side of the equation. I have A inverse, B inverse, A, B, B. And basically here, this A inverse A is going to give me the identity, and I'm going to have what? B, A. And this B inverse is going to give me the identity. And on the right-hand side of the equation, the A inverse A is going to give me the identity. I'm going to have AB, and here, BB inverse is going to give me the identity. And that's just going to give us BA equals AB. And that's what we want to write. We wanted to prove that AB equals BA. Now, the reason why I'm proving this is because I'm probably going to use it later. AB equals BA. So A and B commute if and only if you can distribute the exponent n over top of A and B like that. So AB to the n is A to the n, B to the n. I will use that sometime at some point. Not in this video, in another video. Probably the next video. But before we go on to the next video, we want to do one more exercise. This one's actually in your book. This is exercise 30. Page 202. Section 7.2. This says let A and B be elements of a group G. Show that the order of AB equals the order of BA. This is actually a little tricky. It's tricky. Okay, so we're going to start off by declaring A and B are elements of a group G. we're going to say AB, its order is M, and BA's order is N. We're just giving those numerical designations. So the order of AB is M, the order of BA is N. So what we're going to do first, we're going to show that N is less than or equal to M. That's our first goal. So first, we show N is less than or equal to M. And then after that, we'll show M is less than or equal to N, so that means they'll be equal. Okay, so how do we show N is less than or equal to M? So first I'm going to look at note M is the least positive integer such that AB to the M power equals the identity, right? That's the definition of the order, right? The order of AB is the least positive integer such that AB to that power equals the identity, in this case M. Now, what's AB to the M mean? That means you got AB a bunch of times. That gives you the identity. How many copies of AB? Well, we have M copies. Now, what I'm going to do, I'm going to do an if and only if here. I'm going to focus on the first one, AB. Kind of peel that off the front, or just kind of isolate it. And the others, we'll just let be blue ABs. So how many of these ABs do we have in blue after the green AB? Well, there are M minus 1 of those, right? M minus 1 copies. Why? Because we peeled off one off the front, or we isolated the one at the front. So what does that mean? That means AB times AB to the M minus 1 equals the identity. Now, note that whatever you multiply AB by to get the identity has to be AB inverse. Because this blue thing is actually AB inverse, because we're multiplying the green AB by this blue thing to get the identity. So that means it follows that AB's inverse is this blue thing, AB M to the minus 1, M minus 1. Now something else we know, so when you focus on AB's inverse, another name for AB's inverse is B inverse A inverse, right? B inverse A inverse, we've seen that. So B inverse A inverse equals this blue thing here, AB to the M minus 1 power. Okay. So now what I'm going to do, I'm going to focus on the BA to the M power. BA to the M power. So let's look at BA to the M power. What does that mean? That means I'm copying down BA a bunch of times. How many times? M. M copies of BA. Now what I'm going to do, I'm going to kind of isolate the first and the last. And the others I'll just let be blue here. So the first B and the last A. And that means everything else is going to be a bunch of ABs, right? We're going to have a bunch of ABs. How many ABs are we going to have there in the middle? M minus 1 copies. Why M minus 1 copies? Well, we peel off a B in the front and an A on the back. That means they're M minus 1 ABs. Okay. So I used a reassociation with parentheses. So that means we got what? B. In the middle, we have AB to the M minus 1, right? We have a bunch of ABs, M minus 1 copies. So we have B, AB to the M minus 1, and then A. Now, how about AB to the M minus 1? Well, we said earlier AB to the M minus 1 is a red B inverse A inverse. So I'm going to replace that. I have B, and that blue I'm going to replace with the B inverse A inverse, which we saw earlier. We got the green A, and B times B inverse. That's going to give me the identity. Well, let me do some reassociation first. I'll be a little more careful about this. We'll have B inverse will reassociate first, and then we'll have A inverse A, and then we'll have the identity times the identity, which is the identity. So what do we have? We have BA raised to the m power is the identity. So what does that mean? Well, if you go back to theorem 7, what number was that in the book? 7.9.1. That's the one in the previous video. That means this power here, BA raised to the m power, gives you the identity. This power is divided by the order of BA. What was the order of BA? The order of BA here was n, right? So the order of BA has to divide m. So the order of BA, which was n, that has to divide this exponent here, m. Now, since n and m are both positive, that means n is less than or equal to m. So we've proven n is less than or equal to m. That is what we wanted to do. Right? First, we show n is less than or equal to m. So we're going to do a similar thing to show m is also less than or equal to n. So let's do that. So next, we show. So it's pretty much the same argument, similar argument. Next, we show m is less than or equal to n. To go through almost the same motions, but reverse the roles of B and A. So first, note so we're going to start here with the definition of the order. Come on, there we go. There we go. So we're going to start with the definition of this time. So last time we started with the definition of this. Now we're starting with the definition of order of BA equals n. So note n is the smallest positive integer such that BA raised to the n power equals e. So that means BA a bunch of times gives you the identity. How many copies of BA? We got n copies. That's equivalent to, well, let's peel the first BA off the front. And we're going to have a bunch of additional BAs. How many copies of BA will we have in green here? How many copies of BA in green will we have? N minus 1 copies. Right, because we took one BA, or we isolated one BA on the front. So that's equivalent to saying that BA times BA to the n minus 1 power is the identity. So it follows that BA's inverse is this green dude, BA to the n minus 1. Why is that? Because when you multiply BA by BA to the n minus 1, you get the identity. So BA's inverse is BA to the n minus 1. Okay. So that means, so what's another name for BA inverse? Well, that's A inverse B inverse, right? So that's equal to this green dude, BA to the n minus 1. Okay. So now I'm going to look at AB to the n power. AB to the n power. So I'm going to take AB, raise it to the n power. That means what? AB a bunch of times. AB a bunch of times. Actually, n copies here. And let's kind of isolate the front term, the A, and the back term, the B, and make these others green in the middle. So we have a bunch of BAs in the middle. So we're going to have A on the front, B on the end. We're going to have a bunch of BAs. BA, BA, BA. How many of those? Well, we're going to have n minus 1 copies, right? Because we took off an A and a B on the front and the back. Or we isolated an A and a B on the front and the back. How did that happen? I don't know. That's crazy. All right, that's crazy. So we're going to actually have what? A times BA to the n minus 1 times B. But what's that green BA to the n minus 1? Well, we saw earlier that's that red A inverse B inverse. So we're going to have A inverse, B inverse, B. And then we can just play a reassociation game where we have A inverse, B inverse, B. It's going to give us the identity. That's the identity. That's the identity. So AB to the n power is the identity. So that means the order of AB has to divide n here, right? So it follows that. So by, what theorem was that? 7.9.1. Come on, dude. Work by theorem. 7.91. The order of AB, what was the order of AB called here? M, right? M, if I can get this to right, has to divide this power here, n. So thus, it follows, since m and n are both positive integers, m is less than or equal to n. So what do we have first? We had n is less than or equal to m. Now we have m is greater than or equal to n. Or m is less than or equal to n. Before we had n is less than or equal to m, so therefore, hence, m equals n. That is the order of AB, that's what m was, equals the order of BA. That's what n was. And that's what we wanted to prove. AB and BA have the same orders. AB and BA have the same orders.